Good morning, everyone. Bonjour, bom dia. Ni hao, Professor Wang. My name is Zoltán Kovács. I serve as a general chair now at the ADG 2021. I hope you are well and ready to be here in the morning. Predrag, can you hear me? My voice? Please. Okay, so everything seems to be fine here. And let me quickly introduce the morning program, but before that, very quickly, I would like to give you a link on the yesterday sessions. So this is in the link, the chat. I will copy the link to the sessions for yesterday. Yes, so you will be able to open these files. Both are over 1 gigabyte, and check if you are willing to agree that these files will be published. We will discuss the question tomorrow during the business meeting. The second piece of information is that we collect the slides for your talks, and while some presentations already present also slides here on the web page of the conference, and you can download them and read them more thoroughly if you need some information or you are interested in the topic. So please, if you have finished slides for the next talks, or your slides have been corrected or extended, or if you want to share them just simply, then please send the slides to me or to Predrag or to the conference email address. So another piece of information that we extended the program for Friday. This was the idea from Philip, because he and actually me too, so we miss the personal communication. Only the frontal communication exists now, and because of that we extended the program for tomorrow at 13, so 1 o'clock in the afternoon. After the official closing of the program, we offer breakout rooms for free conversations among ourselves. So if you are not too hungry after the business meeting, please stay for some seconds, for some minutes, and share your thoughts. The breakout rooms will be available only tomorrow, so you cannot see a button in the Zoom system right now, but tomorrow there will be a link, so you just click on it and you can select which room is interesting for you, or you can change rooms as well if you want to meet other people or you want to communicate with other colleagues. So that's all for the morning. Thank you for your kind attention. I hope you will find interesting talks today, and it's my pleasure to give the word to my friend Julien Narbu from France, from the University of Strasbourg, and he will chair the morning session. Thank you.
Okay, thank you, Zoltán. Thank you for the organization of this conference. It's my pleasure to chair this session about formalization of geometry. We will first start with Gilles Dewec. So Gilles Dewec, our invited speaker. Gilles Dewec is a researcher at INRIA. He's also professor at ENS. He leads a deduction team This team developed the system deducti and the project Logipedia that he will talk about, I think, today. But Gilles also many other has done a lot of things. He has written books about philosophy, about computation, logics, language. He is also promoting the teaching of computer science in high school and so on. So thank you, Gilles, for accepting this invitation. I think the ADG community is very interested in this project because for a long time we were trying to make such a similar project but focus on geometry, about writing a formal book about geometry. And the Logipedia project is a much wider scope project, and it will be, I think, of interest of the ADG community to learn about this project.
Thank you very much for your invitation. I'm going to try to share my slides. Okay, can you see them?
Yes, very good.
Okay, okay. So thank you again. The project I'm going to speak about exists because we are facing a new crisis of the universality of mathematical truth. And the reason why we are facing this new crisis is because we have developed proof processing systems. So proof processing systems, any kind of software that can manipulate formal proofs, either build or check or whatever. Formal proof is a huge step forward in our quest of rigor, and they allowed to prove new theorems and so on. But they have also the side effect that we are facing a new crisis of the universality of mathematical truth. So first of all, what is a crisis of the universality of mathematical truth? It is a moment in time when mathematicians disagree on the truth of some statement. So there are not that many crises in the history of mathematics, but I gave on this slide a few examples. Let's say it is a main crisis of the universality of mathematical truth. So probably the oldest one was in the 6th century BC, when the Pythagorean discovered the irrationality of a square root of 2. And we can say that at this time, mathematicians disagreed on the truth of the proposition there exists a number r such that r squared is equal to 2. So of course, from a geometry point of view, the diagonal of a square is such a number. And from arithmetic point of view, there is not two whole numbers, so that the ratio of these two numbers put to the power 2 gives 2, of course. So we can say a few words about the resolution of this crisis. The idea was to replace the word number by two different phrases, so that we can ask two different questions, that there exists a rational number such that r squared is equal to 2, that there exists a real number so that r squared is equal to 2. Another crisis is kind of old as well. It is the hesitation of mathematicians to use infinite sums from Zeno and Archimedes to Weierstrass. And this can be seen as a disagreement on the truth of the statement. The sum from n going to 0 to infinity of -1 to the power n is equal to 0. Of course, the first moment in history when not only mathematicians disagreed on the truth of some statement, but were conscious of living a crisis, was because of geometers, and it is of course a rise of non-Euclidean geometries. that can be seen as a moment in time where geometers disagreed on the truth of the statement, the sum of the angles of a triangle is equal to pi. A century later, there is a similar crisis, which is called the crisis of constructivism. And then mathematicians disagreed on the truth of, for instance, a statement if a set E contains 0 but not 2, that there exists a number n so that n is in E but n plus 1 is not. And of course, if we take the excluded middle as a logical principle, we can prove this statement, but if we don't, we can't. We can also see all the debate about the axiom of choice at the beginning of the 20th century as such a crisis, and we can see this crisis as a disagreement on the truth of the statement every vector space has a basis. Indeed, if you take the axiom of choice, you can prove that every vector space has a basis, but if you don't, you can't. So each time such a crisis was faced, nobody was happy with the crisis, and everyone thought the crisis had to be resolved. And I think it is fair to say that today these 5 crises have been resolved. And unfortunately, we are facing a 6th one. So why are we facing this new crisis? It is because we have developed a lot of proof systems, proof processing systems. So here I speak both of proof checking systems such as Hall4, Isabelle Hall, Hall-Light, Coq, Matita, Lean, PVS, and so on. But also of automated theorem proving systems. And I have to say, I already said that these systems are a huge step forward in the quest of mathematical rigor, and they could, they let us build a proof that could not have been built by hand. So it's no doubt a major step forward in the history of mathematics, but it triggered a new crisis of the universality of mathematical truth. Why? Because before we had such systems, we had a proof of the four-color theorem, and now we have a Coq proof of the four-color theorem. So is this theorem provable as well in Hall-Light or in PVS? This is still a question. We have, for instance, a Hall-Light proof of Hale's theorem. Hale's theorem is also known as Kepler Conjecture, but it's not a conjecture anymore. And we have a formal proof of this theorem, but it is in Hall-Light, so we are not completely sure we can express it in Coq or in PVS. And we have PVS proofs of other theorems. And we have lost the idea that a theorem is proved or not. Now we have judgments such as this theorem has been proved in this system. And each system has its own language to express mathematical statements and each own notion of proof to prove such statements. So we are again in a crisis situation. And this crisis is, of course, the mathematical and the philosophical problem, but it is also a social and industrial problem. So it is a social problem because it is a major obstacle to teach a formal proof. So why would you pick one system and not another? And what you are teaching, is it specific to the system you are using, or is it universal? This is very difficult to answer these questions. And it's also an industrial problem because it is an obstacle for formal proof to be used in industry. So we have to find a way to solve this crisis. And it's a good thing to look at the way crises in the past have been solved. And if we focus on the crisis of non-Euclidean geometries, we see that one way to solve a crisis is to express the axiom of the various geometries. Sorry, there is a typo here. It's not set theories, it's geometries. Of the various geometries, such as Euclidean, hyperbolic, elliptic geometry, and so on, in the same logical framework. And in this case, it was predicate logic, although predicate logic was made precise a century after the crisis of non-Euclidean geometries. But now we know how to express the axioms of all these geometries in the same logical framework in predicate logic. Then we can remark that there are a lot of axioms that are common in the different geometries, and that these geometries differ on a very small number of axioms. And then we can analyze all the proofs that we have written in geometry and ask ourselves what are the axioms that are used in each proof. And in particular, if we do not use any axiom which is specific to Euclidean hyperbolic or elliptic geometry, we have a neutral proof. A proof is a neutral geometry, but some other proofs use the parallel axiom or other axioms. And maybe I have to explain my typo, because this kind of solution has been used to solve the crisis of the universality of mathematical truth triggered by non-Euclidean geometries, but it has also been used to solve the question of the axiom of choice and the last crisis I spoke about, which is the one of set theory. So can we do the same thing to solve the crisis we are facing now? So can we express the theories that are implemented in Holite, in Koch, in PVS, and so on, in a common logical framework, for instance, in predicate logic? And then we would be able to analyze which axiom is used in which proof. And this analysis could be made regardless the system the proof has been developed in. So this is a point that we are attempting to reach. So for instance, if you have a proof that has been developed in Koch, but it does not use all the axioms of the theory implemented in Koch, then this proof should be, we should be unable to export or to use this proof in a different system as soon as this system implements all the axioms that have been used in this proof. So we should not focus on the system the proof has been developed in. We should rather be focused on the axioms the proof uses and on the theories in which this proof can be expressed. So can we do that? Can we express the axioms of all these systems in predicate logic? And in fact, the answer is negative, and this is why we have to focus a little bit on what a logical framework is and how we have to modify predicate logic so that we can carry out this program, this project, but for a different logical framework. So first, we have to remember that in 1928, when Hilbert and Ackermann proposed predicate logic, it was a huge revolution. It was a huge step forward in the history of mathematics, because before that, geometry, arithmetic, set theory, and so on, each of these systems had its own syntax for propositions, it had its own notion of proof, and so on. For instance, there is a very little relation between Euclid's geometry and Peano's arithmetic. They are completely different systems. And the fact that we could express both the axiom of geometry and the axiom of arithmetic and the axiom of set theory in the same logical framework in predicate logic was a huge step forward. In particular, there was only one notion of proof, only one syntax for propositions, and this was very important to bring these theories together. More importantly, maybe, not only we could express geometry and arithmetic in the same framework, but we could express all the geometries in the same framework with or without the parallel axiom and so on. And the same holds for set theory. We could express all set theories with or without the axiom of choice, with or without inaccessible cardinals, and so on, in the same logical framework. But we have to understand that from the beginning, there were limitations of predicate logic. And in particular, in 1928, there were some famous theories, some famous systems, such as geometry, arithmetic, and set theory that have been expressed in predicate logic, but some others have not. And in particular, we had a system which was called the type theory, and that existed since the very beginning of the 20th century. The first paper of Russell about type theory dates from 1902, and this type theory has then been used in the Principia Mathematica. But this theory was not expressed in predicate logic at that time. So it is possible, now we know that it is possible to express type theory in predicate logic, but it seemed that in the 20s, people didn't know that, didn't notice that, and it was kind of difficult. It is still kind of difficult to express this theory in predicate logic. But in 1940, so 12 years after the design of predicate logic, there was another formulation of type theory, which is based on lambda calculus, and that was impossible to express in predicate logic. So why is it impossible to express in predicate logic? Because in the language of type theory, of Church's type theory, there is a symbol, which is a lambda of the lambda calculus, and this symbol binds a variable. And as you know, in predicate logic, there are only two symbols that can bind variables, and they are the two quantifiers, the for all quantifier and the exist quantifier. So when you define your function symbols, the language of terms, then you cannot have any bound variables in terms, in the first order terms, in the terms of predicate logic. So of course you can distort the axioms of Church's type theory so that you avoid binders and you express binders with more complex symbols. But it is at the price of this distortion that type theory can be expressed in predicate logic. And after the 70s, there were many other theories, such as Martin Love's type theory, the calculus of construction, type theory with predicate subtyping. And none of these systems, none of these theories has been expressed in predicate logic. So again, it is possible, if you really want to do it, to express, for instance, the calculus of constructions in predicate logic, but it requires a lot of work, and it requires to distort the calculus of construction so that it fits in this too small framework that predicate logic is. So what are the limits of predicate logic? So first, as I just said, you don't have any bound variables in terms, so you cannot express a term such as lambda xx, which is a function that maps every x to x, so the identity function. So there is no syntax for proofs, and this idea that the proofs were mathematical objects and that there should be in a logical framework a syntax to express proofs exactly in the same way as we have a syntax to express terms or propositions, dates from the 60s, and of course in the 20s, when Hilbert and Ackermann developed a predicate logic, they didn't have a clue about it. So in this sense, predicate logic should have evolved in the 60s to include a syntax for proofs. There is no notion of computation. So for instance, when you express arithmetic in predicate logic, and you want to know if the proposition 4 times 7 is equal to 28 is true or false, you can give a proof of this proposition 4 times 7 is equal to 28, but you cannot just say, well, multiplication is an algorithm, so all you need to do is to multiply 4 and 7, and you will get 28. There is no notion of computation. Maybe a more technical point is that there is no good notion of proof reduction, but I'm going to skip this. And the last limit, the fifth limit on this slide, is that predicate logic is classical and not constructive. So you can express in it classical proofs, but not constructive proofs. And of course, you can design another logical framework, which is constructive predicate logic, but then you cannot express classical proofs in this framework. So we are not the first ones to have noticed these limitations. And since the 80s of the 20th century, there have been several attempts to modify predicate logic to address these limitations. So the question of bound variables was the first to be addressed, and logical frameworks such as lambda prolog, Isabelle, or the lambda pi calculus allow to extend the syntax of terms with binders. A syntax of proofs was introduced in the lambda pi calculus, and the lambda pi calculus is also known as the Edinburgh logical framework. And in this system, this system is the first logical framework where there was a syntax for proofs. The question of computation and of proof reduction was addressed in a completely different logical framework, which is called deduction modulo theory. And deduction modulo theory is just an extension of predicate logic where you can define a theory with axioms, but also with computation rules. And the integration of classical and constructive arguments in the same framework led to what is now called ecumenical logic. And the lambda pi calculus modulo theory is another logical framework that generalizes all these logical frameworks: lambda prolog, Isabelle, the lambda pi calculus, deduction modulo theory, and ecumenical logic. And it can be seen as a mixture of the lambda pi calculus and deduction modulo theory, hence its name, the lambda pi calculus modulo theory. And we understood after that we have proposed this framework that there was a very similar framework that was called the Martin-Löf logical framework, which has nothing to do with Martin-Löf type theory, except that Martin-Löf type theory can be expressed in Martin-Löf logical framework. There are a few differences, but the ideas are really the same. And deducti is an implementation of the lambda pi calculus modulo theory. So let me give you a flavor on the way we can express axioms in deducti. And first of all, deducti is a much weaker framework than predicate logic. So there is no primitive notion of term, and there is no primitive notion of proposition, and we have to build these notions in deducti. So to build the notion of term, all we need to do is to introduce a new constant, which is called iota, and it is a capital iota that you can see on the first line, on the first line in the middle part of this slide. And here we declare the constant iota to have the type. So iota is a type constant. And as you see, iota is in blue, and this means the symbol iota is part of the theory we are currently defining. And the constant type is in black. It means it's a keyword of deducti. And as you see, the column expressing that iota has type, so iota is a type constant, is as well in black. So this column is part of the syntax of deducti. So this is enough to declare then for each function symbol a constant of type iota, arrow iota, arrow iota, as many times as you have an arity in this constant. And you see that every term of predicate logic can be expressed as a term in this lambda calculus of type iota. We can do the same thing for propositions. So we introduce a constant prop that is also a type, and it is a type of propositions. And here we need to introduce for each predicate symbol a constant of type iota, arrow iota, arrow iota, arrow prop. For instance, equality has the type iota, arrow prop, so that the proposition 0 is equal to 0 has type prop. We also need to introduce the connectors and the quantifiers. And for instance, we can introduce the implication that obviously must have the type prop, arrow prop, because it takes two propositions as arguments and it returns a proposition. And we can also introduce the quantifier, such as the for all quantifier here. And you see that it has a type which is slightly more complex, and it is because this constant binds a variable. And here we are using an idea that dates back to lambda prolog and Isabelle, which is called higher order abstract syntax, and it is a way to express terms with bound variables in lambda calculus. So as you are geometers, you are maybe more interested in many sorted predicate logic than in one sorted predicate logic. And if you want to have predicate logic with a finite number of sorts, it's very easy. You just replace the constant iota by as many constants as you like, and you can call them iota 1, iota 2, iota n if you like. If you want to have an infinite number of sorts, then it's a little bit more complex, but it is also possible, and I'm not going to explain how, but if you want, we can discuss that either offline or in the questions. Okay, let me say a few words about the way we can express proofs in deductive. And here I will assume there's some familiarity with the so-called Curie-Howard correspondence or Curie-De Bruijn-Howard correspondence. So if you're not familiar with this, maybe this line on the next one will be a little bit esoteric, but you can wait for 2 slides and then it will become clear again. So if we take a proposition such as P implies P, the Curie-De Bruijn-Howard correspondence tells us that the proofs of this proposition, P implies P, should be terms of type P implies P. But this is not possible in deductive because P implies P has type prop, as we have seen, and prop has type type. But P implies P itself does not have type, so it's not itself a type. So there is no way there can be a term of type P implies P. But what we can do is to introduce a new constant proof, which has type prop arrow type. And here we are using the fact that in the lambda pi calculus modulo theory in deductive, we have dependent types. So here it is a type family indexed by propositions. And this constant maps every proposition to the type of its proofs. So if P implies P has type prop and not type, the term proof of P implies P has type, and it may, so it means that there may be terms of type proof of P implies P. So again, following this idea of the Curie-De Bruijn-Howard isomorphism that comes from another 3-name concept, which is called the Brouwer-Haitink-Kolmogorov interpretation of proofs. It's too many names, but the idea is very simple. It is that a proof of A implies B is an algorithm that maps proofs of A to proofs of B, and in particular, the identity function over the proofs of P, so the function that maps every proof of P to itself, should be a proof of P implies P. But here we see that in the lambda calculus, in deductive, this term, lambda xx, where x has type a proof of P, has the type proof of P arrow proof of P. It is a function that maps proof of P to proofs of P. And it should have the type proof of P implies P because we want this function to be a proof of P implies P. But it doesn't. So it means that we have to identify the 2 terms, proof of P implies P and proof of P arrow proof of P. And this can be done in deductive because we have computation rule. So we have to add a computation rule that defines the proofs of P implies P to be functions mapping proofs of P to proofs of P. And this is what we do with this reduction rule, this computation rule. Okay, so this is it for the expression of proofs. And we have seen a few axioms. We have seen already the axiom iota, which is just the declaration of the constant iota, the axiom prop, which is just the declaration of the constant prop, the axiom implication, which is both the declaration of the implication symbol and this reduction rule that we have here that expresses the meaning of this implication, and this declaration together with this computation rule makes an axiom. And we have other axioms that we can express in deductive, so I'm not going to detail each of them. So we have axioms to define the connectives and quantifiers, such as disjunction, the existential quantifier, and so on. We have axioms to express proposition as objects and functions, as in Hall light or in Isabelle Hall or any implementation of Hall. We have axioms for dependency, for object level predicative polymorphism, for object level dependent types, for predicate subtyping, for infinity, and so on. And here are 44 axioms that we can express in deductive. So you can count that the number of axioms in this picture is 44. And so you may think 44 axioms is a lot, but remember that you already need 20 axioms just to reconstruct terms and propositions. So it's only 24 axioms more. So let me give you an intuition about what these axioms do. So in the center, you have the axiom that we have seen, an iota, prop, proof, and you have also set, element, and lowercase iota that are here to express, if you want to express an infinite number of sorts, but we didn't discuss them. Then you have the implication and the for all quantifier. And this is the brown rectangle in the center of the picture. And this is a reconstruction of minimal predicate logic within deductive. If you go north, you have another brown rectangle where you have introduced connectives and quantifiers such as true, false, negation, conjunction, disjunction, and so on. And this is a definition of constructive predicate logic in deductive. And if you go in even further north, you see that you have the classical connectives and quantifiers. And here you have a reconstruction of classical predicate logic in deductive. Now, if you go east, you see that you have two axioms, omicron and arrow. And this is what you need to extend minimal predicate logic to build a simple type theory, which is implemented in Isabelle Hall, in Hall 4, and in Hall Light. And again, you have in orange three rectangles that corresponds to minimal, constructive, and classical simple type theory. Now, if you go south, you get you have 5 axioms that are here to define object level polymorphism, and together with classical simple type theory, you get exactly the system which is implemented in the Hall Light system or in the Isabelle Hall system. If you go on the southeast, you have 5 more axioms that are here to express a predicate subtyping. And this is what you have in the PVS system. So the PVS system is all these axioms we have spoken about, plus these 5 axioms. Now, if you start again from the rectangle in the center and you go west, you have 3 axioms here. And 2 of them, the dependent arrow and the dependent implication, replace the implication and the arrow. And you have and the third one is a similar one. And you have in the pink rectangle the axiom that defines the calculus of constructions. Now, if you add to the calculus of constructions predicative polymorphism, which is on the south, you get kernel of the Koch system. And you have more axioms we didn't discuss. On the northwest, you have the axiom of infinity, which in our case is 4 axioms. And in the southwest, you have axioms that define dependent types. So you have them in the Koch system, but not for in other systems. So this theory is called the theory U, and with a glimpse of hubris, we call it the universal theory, because all the proofs expressed in Hall Light, in Isabelle Hall, in Hall 4, in Koch, in Matita, in Lean, and in PVS fit in this theory, but always they fit in a sub-theory of this theory. Of course, there are other axioms that we can add for universes, universe polymorphism, inductive types, co-inductive types, and so on. And I'm not going to speak about this axiom, that this would be extensions of the theory U. Now, let me discuss a little bit, I'm reaching the last part of my talk, how we can use this theory in deductive to do some reverse mathematics. So we have seen that the calculus of constructions can be expressed with 12 axioms. And minimal predicate logic is a subset of this 12 axiom, which is formed with 8 axioms. So you have 4 more axioms in the calculus of constructions, but you have the same 8 axioms in minimal predicate logic and in the calculus of constructions. So this means that without a surprise, all the proofs that are expressed in minimal predicate logic can be translated to the calculus of constructions. And also that all the proofs that can be expressed in the construction that do not use these 4 axioms can be translated to minimal predicate logic. But not the other proofs. Of course, if we have a proof that genuinely uses one of these 4 axioms, it cannot be translated. Exactly as if you have a proof in ZFC that genuinely uses the axiom of choice, you cannot express it in ZF. Or if you have a proof in hyperbolic geometry that really uses the axioms of the specific axioms of hyperbolic geometry, you cannot translate it to Euclidean geometries, and this is more a good point than a limitation. So here is an example of a huge project that has been carried out by Pierre Boutry, Ferret and Géron, Gaspard Ferret and Johan Géron, sorry. So Pierre Boutry, a few years ago, took the first book of Euclid's Elements and expressed this in Coq, of course in Coq, plus the axioms, the Euclid axioms. And of course, Pierre did many other things, but I will focus on this part of his work, which is the formalization in Coq of the first book of Euclid's Element. Then Pierre, together with Gaspard, they translated this Coq proof into deductive, but now it was expressed in the theory in deductive that corresponds to Coq. Of course, the proof is coming from Coq, so the proof was expressed in deductive with the axioms defining the theory implemented in Coq, plus, of course, the axioms of geometry, Euclid's axiom. And then this year, Johan Géron took this proof and understood that morally, this proof could be expressed just in predicate logic, which is 8 axioms instead of 12. So what Johan noticed was that the 4 axioms that are in the calculus of constructions, but not in predicate logic, in minimal predicate logic, were not used. In fact, they were used in the proofs built by Pierre because Coq cannot avoid using these axioms, but they could be removed. So let me just give you one example of something that was in the proofs of Pierre and translated by Pierre and Gaspard. It was the fact that in the calculus of constructions in Coq, you can express that 2 propositions are equal. So if you have 2 propositions, you can put an equal sign between them, and you get a proof of, and you get a new proposition. Of course, you cannot do that in predicate logic. So Johan had to remove all these equalities and replace them by implications or reverse implication or equivalencies, depending on the cases. But once we had this proof in deductive, but not in the theory expressed in deductive, which expresses the axioms of Coq, but just the 8 axioms of predicate logic, it was possible to translate these Euclid elements to 7 systems that are the systems here, of course, with the axiom of with the Euclid's axioms. So here is the same thing said as a picture. So on the very left, you have Coq. So almost all proofs of Coq, and the goal is that all proofs of Coq should be translated to deductive. So deductive is this big ellipsis in the center of the picture. And they are first translated into a theory expressed in deductive, which is a 12 axiom theory expressing the formalism implemented in Coq. Then you have this partial translation from Coq in deductive to predicate logic in deductive. It is partial because it does not always work, but it worked for all the axioms, all the proofs of the first book of Euclid's Element. And once you have it, you can export your proofs or your library in all the systems that are on the right-hand side of the picture. Okay, so I'm reaching the end of my talk, and I want to say that first, François Thiré did the same thing slightly before with the arithmetic library of Matita. So now both the arithmetic library of Matita and the first book of Euclid's Element are available in these 7 systems. And these 2 steps are the first steps of the constitution of a shared library of proofs, which is called Logipedia. And what we want to do on the long term, of course, is to replace all the libraries that are distributed with the proof systems with a single one that would be online, and that would be this Logipedia library, where proofs are independent of the system used to build them. So whether you use the Coq or Matita or whatever, or PVS, or even if you used automatic theorem prover to build your proof, they are welcome in Logipedia. But they should be presented in a way which is independent of the system they have been developed in. But they should not be independent of the theory that is required to express them. So we want to have metadata that expresses what theory is required for each proof, independently of the system in which it has been developed. And this is one objective of the COST project, which is called EuroProofNet, and that it is about to begin. And this project is coordinated by Frédéric Blanqui. And of course, it is a project where everyone can contribute, whether you're part of the net of the project or not. So what should you do to contribute to this project? You should first develop a small or large library with proofs, and I think you all have done that already. Then you have to translate your library to Deducti. So you can either use an existing translator or develop your own. So we have translators for Coq, Matita, the whole family, and also from first order theorem provers, automated ones such as Zenon and various several others. So if you're using a system that is not, for which there is no translator, you can develop your own, and of course we can help you to do that. Then you have to eliminate the superfluous axioms in your proofs. Maybe there are no superfluous axioms if you're lucky, but maybe there are. And then you can add these proofs to Logipedia, and for this you still need a little bit of help from us, because Logipedia is not. You cannot just upload your proofs in Logipedia. We have to do it with you, but it is a very small part of the project. Thank you very much.
Okay, thank you, Gilles. It was a very interesting talk. We are lacking time, so we have time only for 1 or 2 questions. So I see maybe Jacques is raising his hand. And Jacques, you want to ask a question?
Oh, I wasn't raising my hand, but I can ask a question. Hi, Gilles.
Hi, how are you?
Can you remove the cap? Hi, I'm fine. I was wondering, so this is a grand, ambitious project. How long do you think you can have something which is, you think is viable? How long, in how many years? Or
So obviously it's a lifetime project. You need one life to do that, but we can have more modest objectives. So if your objective is to have the first book of Euclid's Element, it's already done. If it is to have the proof of Fermat's little theorem, it is already done. What we are aiming at now is to have the whole mathematics that are taught in undergrad at the undergrad level. So things like the derivative of the sum is the sum of derivatives and so on. And I believe that we can express that in many different systems. It is not specific to, you don't need 42 universes to prove this theorem, of course. So this, I guess, it is for 3 years to 5 years project. And then if you want to have every theorem that has been published in mathematics, maybe it will be a little bit longer. But now we are aiming at having formalized a trivial mathematics that we teach at the undergrad level.
Yeah, it does. I mean, it's very ambitious. So I guess in some ways the lean people are also targeting a bit of that for their math lib, aren't they, in terms of
yeah. So there are various projects to write books where maybe not every proof is formal, but every statement has been formally proved. And so you're part of one of these projects. So we are obviously, if we look at the proof that are now already in the libraries of Hollight or Isabelle Hall or Koch or Lean or whatever, we have all these theorems. So there are very few theorems that are taught at the undergrad level and that we do not have, but we have to put them in some order. And I guess that also we need to be careful of sharing these libraries across systems, because in particular, if we want students to use that, we cannot say to the students, well, if you want to do formal proof, it has to be Isabelle Hall, okay? And it cannot be, it has to be Koch as well. So when we teach programming languages, of course, we use one programming language to start with, but we tell the students that the programming language we use are Turing complete, and we have no such notion for proof systems. So the only way we can deal with it is to say, well, we do not have a notion of Turing completeness, but our library is checked in at least 12, 15 different systems. So it is the best we can do to approach, to mimic this notion of Turing completeness at a very practical level.
Yeah, I agree with you. Thanks.
Okay, thank you. I'm sorry, but we are already 10 minutes left behind schedule. So I think we will keep the other question for offline discussion. Now we have a talk by Richard Smonton, Jack Palmer, and Jack about formalization of Minkowski spacetime. Who is giving the talk? It's Richard, I guess.
Yes, okay. It'll be me.
Thank you. Can you share your screen?
Yes. Can you see that?
It's okay, yes.
Oh, okay. Hello. I'm Richard. I'm going to be talking to you about some work that I did with Jake and Jack over the past few years. This started with Jake's MSc project and already led to a presentation at ADG 2018, so maybe some of you have seen that. And it's about formalizing an axiomatic system for Minkowski spacetime. The axioms are more geometric than you would be used from the standard physics formalism. And this is based on a monograph published by John Schutz in 1997. And these axioms are independent, which is a point that Schutz emphasizes a lot. So I'm going to be talking about spacetime and why we want to formalize it as we do. Then I'm going to be talking about the formalization that we did. I'll give you some of the axioms of Schutz and some of the theorems that we have proven. And then I will talk about how we proved, in particular, the harder theorems by using symmetries and reasoning without loss of generality. So in physics, in normal undergrad physics courses, in special relativity, you define spacetime as R4. So it's just a four-dimensional kind of Cartesian space with a Minkowski metric on it. And this is nice on one hand, because you have a lot of mathematics at your fingertips. You can just always assign coordinates, and then you do linear algebra, you crank your machinery, and you get almost any answer that you can be looking for. The disadvantage of this is that the entire language of formulating physics is entirely mathematical. There is no direct relation to any kind of real-world experience, any kind of physical experience that we might have as humans. So it's not very intuitive. Probably since spacetime was first thought about by Minkowski, but definitely since the 1930s, there has been work trying to build an axiomatic spacetime in the way that Hilbert approaches Euclidean geometry in his Grundlagen der Geometrie. And hopefully the hope is that this will lead to axioms that are closer to physical intuition and therefore have a large pedagogical benefit. So the primitives that we use, or that Schutz uses in his system, is just a set of events. So that's things that, well, it's points in a four space. So it's points in space and time, and then a set of paths, which can be thought about as the physically viable histories. So each set of path, so each path is a set of events, but not necessarily each set of events is a path. And then there is the last primitive is betweenness, which is a ternary relation that acts on events. And you can think about it as one thing being between two others. So in our formalization, this is just a slide to show you some of the proof effort that we go through. I've taken here part of a proof of a theorem on linear order that gets split into 3 cases. And you can see here, the first case is about 3 lines long in the prose, and it takes us 95 lines to prove it in Isabelle, in the higher order logic instance of Isabelle. The second case is much larger already in the prose. It takes about 9 lines, and it takes us about 500, including all of these additional results, which is mostly because Schütz starts by saying, let k be the smallest integer, and we have to prove that this k exists, which is not actually that trivial. And the shortest case in the prose is also the shortest case in our formalization, which is quite nice. And it's this second case here, which Schütz essentially leaves as an exercise to the reader by saying it's similar to case 1. And we use an explicit symmetry in order to use case 1 to prove case 3. Another proof is given here. You can see it's 3.5 lines, but again, it takes us this is roughly 500 as well. And that's because in this case, we have to talk about without loss of generality theorems that, of course, in informal maths are done a lot quicker. Our De Bruijn factor across the entire formalization is about 24. So each line of prose produces about 24 lines of code, but this is heavily skewed towards the latter formalization. So the latter proofs are much longer. These are some of the axioms that we have. The axioms of order are quite similar to some other geometries that we've already heard about yesterday. So I'll only insist on O2, which gives us a symmetry in betweenness, so that if the ordering ABC holds, then CBA must also hold, and O4, which gives us a kind of transitivity. One of the fundamental things that we will talk about a lot are chains. A chain is a set of events that is indexed with natural numbers starting from 0. This could be either finite or infinite, and a set of adjacently indexed events. So if 3 events have adjacent indices, then they must obey this betweenness relation. So it's kind of like an ordering map from the naturals into events. We also have some axioms of incidence, which again are similar to what Patrick was talking about yesterday, I think. And the more important ones of these for special relativity are those relating to unreachable sets. So unreachable sets are where we stop being a Euclidean geometry with just Galilean relativity. So Galilean relativity is where if you're moving at a certain speed v away from me and you throw a ball away from me at speed w, then I would expect to see the ball at v plus w. But this doesn't hold in special relativity. And the way we do this is by saying that certain events should not be connected by viable physical histories to the point that I'm at right now. And it's not enough to exclude just one event, because if I say I'm at a point A and there's a path P that is a physically viable history, and there's just one point B that I cannot reach, then that's, I could be cheeky and I could say, well, that's just the point that it would take me infinite speed to get to. So that doesn't make this special relativity. But excluding 2 events means that there must be an event at a finite speed that I cannot get to. So we've just introduced a finite speed limit, which is really the central tenet of special relativity. Yes, and unreachable sets have nice properties of connectedness and boundedness as well. So these are just some theorems to show you what kind of geometry this leads to. We have 2 Culinarity theorems to extend our version of the axiom of Pasch, and it just says that diagrams like this make sense, so that if you have a triangle ABC and you have a blue path here hitting this triangle ABC, inciding on this triangle, then it must meet this triangle in a point F if these points D and E exist, and furthermore F must be between A and B, and these 3 points must be ordered DEF as well. Also, we prove that paths are infinite, which is again a result that you would intuitively expect to hear about. Notice the caveat, this is just a pretty weak infinity. It doesn't say anything about density, and it only says that this is at most countably infinite. Sorry, at least countably infinite. So back to chains. So you can see that if we have this indexed set, we can talk about the function that takes an index to the event indexed by this function. And we need to do a lot of proofs about this function because the informal mathematical notation that just talks about events that are indexed doesn't work very well in Isabelle. So we do direct proofs about this function. For example, that this function takes any set of indices that are ordered in the natural numbers to ordered events. And this is not just adjacent indices. So this kind of generalizes the transitivity axiom. We also prove, for example, that this function is injective. And we can then generalize this result on ordering on a chain to talking about ordering on paths. And this is one of the central theorems that we prove, and it says that any finite subset of events on a path must also form a chain, i.e. must be linearly ordered. Good. Yes, I will revisit the proof of linear ordering and then proof about boundedness. And I'll talk to you about how we proved them by using explicit symmetries and this without loss of generality in the form of special lemmas. This is the symmetry we use in particular. You can see it takes a function f that indexes a set of events x into a chain, and it says that you still get a valid chain if you take a reversed function. So you basically take f, but you start counting from the other end. And this must still give you a valid chain. So that's generalizing the O2 symmetry that was in the axioms for betweenness. And the way that Schütz proves his theorem of linear ordering on path is by taking a chain and then inductively appending an event E. If you do that, you can either append it on the left, you can append it on the right, or you can append it in the middle, and we'll ignore this middle case for now. But say you've proven that you can append on the left and you still get a valid chain. Then Schütz says, well, appending on the right is similar, and I'm going to let you do it yourself. But we can't say that to Isabelle. So instead what we do is that we obtain the reversed function by using this chain symmetry lemma, and then we use this reversed function to append an event on the left, which gives us a valid chain by this case 1, and then we reverse that again. So it's really a little bit like a switch of basis. Yeah, and that's explicitly using a symmetry in order to make explicit what Schütz meant when he said this is similar. There is a kind of a converse result to the chain symmetry, which is that this reversed version is the only other valid chain on that same set of events that you could have, which we also prove. This is not a result that Schütz proves in his monograph. And it makes it very obvious that talking about events is not enough to talk about chains. You really need this function. And we have to even use that in a proof of a theorem that follows the prose very closely in order to fill in a point where the original mathematics just forgot about the possibility of there being a second chain on the same set of events. Now I'll be talking about maybe the best bit of this talk, the without loss of generality lemmas that we used in order to formalize some of the kind of intuitive geometric reasoning that Schütz uses in his later proofs. So without loss of generality is used in pen and paper proofs quite frequently. You often read it in maths textbooks. It's not always very formal. It often encompasses different symmetries, and it's not always very clear which symmetries they are. It's not always very explicit which symmetries these are. And they might be symmetries at different levels of reasoning as well. So this is obviously very hard to mechanize for that reason. And you could either replace such without loss of generality reasoning by just copy pasting a proof that you've already done, much like you might have done in the proving case 3. You could have just proven case 1 in the stuff that I showed you just now. You could have copied the proof of case 1 and then adjusted all of the orderings, and it would have probably given you something fairly similar, and you do a bit of adjusting. You could also use intermediate lemmas, which is what we did. We had this chain symmetry lemma, and then we used our case 1 as a lemma with variables in order to apply this symmetry to get our new result as well, our reversed result as well. Or you could explicitly identify the symmetries that are being talked about, and you can try and put them into a lemma that is this vlog lemma that I will be talking about. So we have several of these lemmas that apply at different levels of generality, and also for different cases of distinctness and degeneracy of the events they're talking about. I'll get to that in the next slide. There are already examples of such vlog lemmas in the ordering theory of Isabelle. we try to follow a similar structure. So you can see here in red, it gives you some symmetries that you assume to be true about a predicate P. So in this case, P is symmetric and it's reflexive. And then in blue here, it identifies a kind of a sufficient case, so that if you establish that PAB holds in this sufficient case, then that's enough to show that in general PAB must hold. So we follow, you can see our vlog lemmas are a little bit bigger, a little bit more complicated. This is partly because we have properties that apply to sets of events and events. So there's a lot more naming going on here. It's also because we have two relations. We have this is-int relation, and we also have a relation P that we want to do proofs about. But it follows pretty much the same style. It says that P has some symmetry that we want to use, namely it is symmetric in exchanging its variables, in exchanging its arguments. And then it identifies the sufficient cases, these essentially distinct orderings that are enough to consider. You only need to consider these 3 cases instead of the entire 24 permutations that you could otherwise get. And even if you considered permutations modulo the O2 symmetry that we've already established, you'd still need to consider 12 cases. So really, this is quite a large reduction in how much proof you need to do. Yes, right. And so the structure of this lemma with these essentially distinct cases is mirrored when you try to do proof using a vlog lemma. So you start by stating a desired result. This is kind of an outline of a proof as you might do it. So you want to say you want to prove that the intersection of 2 intervals is also an interval. Then you use a kind of symmetry result that I've not talked about here, namely that if I1 intersection I2 is an interval, then I2 intersection I1 is also an interval. Once you have this, you identify the proposition that you want to prove things about, which is this here. Notice we've had to add the empty set to do some bookkeeping. And then once you have that, you just look at your vlog theorem. You look at which 3 cases you need to talk about. You fix these orderings. You name the events, and you fix their orderings. And then you can see you can explicitly prove just a part of this proposition. And you can explicitly use these events that you've already fixed to say, for example, I intersection J is the interval between C and B. So it must be an interval. And these 3 cases are then enough for Isabelle to very simply prove that this must hold in general using your vlog lemma. There are some references here. This is our AFP entry where all the formalization is. This is our archive preprint where you can read a lot more detail about the formalization. And then this is the venerable monograph by Schütz, which is of course central to our work. I'm not going to talk about the summary, and some directions we would like to explore in the future, or might possibly explore in the future, is to continue the mechanization, notably the theorem of continuity, and continuing with the next chapter in Schütz's work. And then also extending the generality of vlog lemmas, and perhaps identify those bits of it that don't actually need to know about what the symmetry exactly does, and perhaps even go towards some kind of automation, although I know very little about that as of yet. Thank you very much. I'm going to leave this slide open while I take questions. Thank you for listening.
Okay, thank you for this interesting talk. So do we have questions? Yes, Zoltan?
No, I don't have a question. Sorry, maybe.
Oh, yes, it was, sorry, I had the wrong icon. I do have questions, so if nobody wants to ask, I can. The first one is maybe inspired by the talk by Gilles, is you are using natural numbers. Is it really necessary, or you could have an alternative formalization without using the natural numbers for indexing the path?
I think what we really want to use the natural numbers for is because they have a well-established linear order. So we're really looking for a way to talk about kind of orderings that aren't just about adjacent events. So the natural numbers are very nice because you can talk about this function that is, you can now talk about a set of events that is order isomorphic to the natural numbers. And this is a very well-defined, well-understood concept that has a lot of results about it already.
Do you need the principle of induction in natural numbers?
We do need induction, yes.
Okay.
Schütz uses induction quite a lot.
Okay.
Yes. So in fact, the natural numbers are the least of our assumptions here. In general, the theory by Schütz relies on the consistency of the real numbers as well.
Someone wants to ask another question? I can't see raised hand. So I have a second one. If you rename some of your concepts like path by line, you see that a lot of the axioms are shared with Tarski's or Hilbert geometry. And there is previous work on formalization of geometry. Did you try to reuse part of this formalization?
Yes, so we do actually reuse, in particular, this whole idea of the indexing function comes out of the PhD thesis of Phil Scott, which was about ordered geometry in Hilbert's Grundlagen. And that's almost the same definition that we have now for chains. So yes, it is very much inspired by in particular his work on Hilbert's geometry. Since we share the axioms of order, at least partly, and some axioms of incidence, yes, you would really expect that a large part of our geometry is shared by other geometries. I've also noticed that some of the results that he proves, we also prove. So, for example, this there is a reversed chain, and there is a unique valid chain on sets of events can be found in Hilbert as well, where it's also an offhand comment. He kind of says, well, this is obvious. It's left as a proof to the reader. And that appears in Phil's thesis, yes.
Okay, so thank you. Is there other questions? No, so we can keep a 10 minutes break, and we come back at 11:20 for the talk by Nicolas Magot about spreads and packing in projective geometry. So let's go for a break. Thank you.
Hello.
Okay, thanks. So it's my pleasure to welcome Nicolas Magot, who will give a talk about formalization of spreads and packing of PG32. Okay, so go ahead, Nicolas.
Hello, everybody. Can everybody hear me? Because I'm not sure. Can you just, someone can just tell me they hear what I say? Yeah, okay. Thank you very much. So I'm going to talk about spread and packing in the framework of the smallest projective space, PG32. So you can see a picture here of what PG32 looks like in reality. Okay, how do I change page? Okay, so first I will remind you what projective geometry is, and especially what are the axioms in 3D context. And then I will talk about some data structure for finite projective geometry we choose to use in the Coq-proof assistant to make the proofs. And then I will give you a few results about the spreads and packing in this particular projective space. And finally, I will discuss what kind of formal proof we achieved and what is currently going on before concluding. Okay, so as you may already know, projective geometry is based on incidence geometry. It means we just consider points, lines, and an incidence relation. And when we go from incidence to projective geometry, in 2D, we consider that two lines always intersect, and in 3D we have Pasha axiom, which I will present in a few minutes. And the main advantage is that it's a very simple description. It only requires 6 axioms to capture the essence of a projective space geometry. So the goal of this talk and this work is to present how to specify some finite model of projective geometry to formally check all these axioms I talked about before, and to compute spreads and packing, and then prove some of their properties. And finally, this boils down to taking Coq to its limit with respect to specification and also with respect to proof, where we reach the limit where Coq might succeed or might not, and we have to turn around and find an alternative way to do things. Okay, so the object we handle are points and lines. So they are described as parameters in Coq, and we also have an incidence relation, which is called incid LP for line point. And we have some Boolean equalities on point, on line, and we have some all distinct predicates, which are distinct 3P, 4P, and we even have a distinct 5L, which is a predicate which says that given 5 lines, they are all distinct, it will be useful in the spread computation. And we also have a notion of intersection, so the usual stuff. The axioms of projective geometries are as follows. The first axiom A1 says that through 2 points, there is 1 line. The uniqueness axiom says that given 2 points and 2 lines, if 2 points are both on both lines, either they're equal or the lines are equal. Pasch axioms will be seen in a minute. And all the other axioms, first of all, we say that each line that at least 3 points, there exist 2 lines which do not intersect, which ensures that dimension is greater than 2. And the last axiom bounds the dimension and says that given 3 distinct lines, there exists a 4th line which intersects all the 3 previous ones. So Pasch axiom is this axiom here, where you consider, for instance, lines A, B, and CD, and these 2 lines, they do intersect in G. And if these 2 lines intersect, then lines AD and BC intersects in I. Okay, so the axiom can be described directly in Coq using this specification here. And what's important to notice is that there are lots of universal quantification and existential quantification. So when we will consider finite spaces and we like to make case analysis on points and lines, it will be very costly. See, for instance, axiom A2, let's consider 4 points and 4 lines. And the axioms for dimension, it considers 3 lines, and then it builds 1 line and 3 points. So it's a very heavy computation. Okay, so to fix the idea, let's remind you what are the dimension of finite projective spaces of the form PG3Q. So for PG3Q, which we consider there are 15 points and 35 lines with 3 points per line, and you see that it grows quite quickly. And what is a bit difficult is that even the smallest projective space is already quite big with 15 points and 35 lines. If you take a relation which says something on points and lines, it's already huge. By duality, you have a same number of points in line, data structure. So when it comes to considering data structure, you have several choices. One of them will be to use finite set as proposed in SS Reflect, for instance. But this data structure, it's a bit difficult to handle when you want to do a case analysis on it. And it's rather slow, and we'll face some performance issues because we'll have several case analyses to do on lines and points. So we need the fastest possible data structure, and the fastest possible data structure is the following one, where we consider points and line as simple inductive types. So in this case analysis is very easy. So the definition consists in taking one inductive point. It is defining point as a series of constructor with no argument, P0, P1, P2, up to P14. So you can imagine it's a bit boring to write, and it's even worse for line. And you imagine you try and write the incidence relation, it's a bit more complete. It's very tedious as well. So we choose to have an automated tool, which once we provided the incidence relation as the list of points belonging to one line, it builds the incidence relation as well as all the properties for all the axioms. Say the axiom that states that given 3 lines, there exists a 4th line which intersects the 3 previous lines on 3 different points, on 3 points, which may not be different. We compute all these points in advance, and when we do the existential proof, we just call the function, which is kind of a Kolmogorov of the statement, and we get the result immediately. So this is the approach we find the most practical, because we have an automated tool which will generate the specification, which would be impossible to write by hand. And it makes doing case analysis and proofs faster, which is one of the bottlenecks of our work. Okay, so to sum up, you have here the definition of points, then the definition of lines, and then you have a match construct to filter the points. So you say that in L0, you have P0, P1, and P2, and so on. And then the function for axiom F33, it just makes case analysis on the 3 lines and provides a solution which will be directly fed to Coq immediately. So this function F33 is very huge, and it takes a while to be accepted by Coq, but then once it's accepted, it makes the proofs straightforward. Okay, so if we go to the center of this talk and talking about spreads and packing, so I will start by reminding you what spreads and packing are. So a spread in PG3Q is a set of Q of the square of Q plus 1 lines. So we choose Q to the power 2 plus 1 lines, and we choose these lines to be pairwise disjoint. And so we want to make a partition of a set of points. So we have Q2 plus 1 lines, and it builds a partition of a set of lines. So in PG3Q, it consists to some sets of 5 lines. Sorry, I just have issues reading numbers directly in English. And the packing is the same thing, but instead of considering set of lines, we consider set of spreads. And so packing in PG3Q is a set of the square of Q plus Q plus 1 spreads, which are also pairwise distant and thus partition this time the set of lines. And in PG3Q, it corresponds to sets of 7 spreads. So imagine a spread is already a set of 5 lines. So you have a combinatorial explosion, which makes things much bigger. So there are some well-known results about the spreads and packing of PG3Q. So the first one says that there are 56 isomorphic spreads in PG3Q, which means you can generate, if you consider spreads ordered where the lines are ordered in the natural order L1, L0, L1, L2, and so on. And you have 56, and they are all isomorphic in a sense we'll detail later. There are 240 packings in PG3Q up to isomorphism, same idea when the spreads are sorted in the packings. And these 2 packings, they can be divided into distinct equivalence class, each of them having 120 packings. All the details of this statement can be found in the book of Hirschfeld, which is quoted here. So what we achieved, oops, I'm stuck, no. So from the formal proof side, what goes on? So we defined formally what spreads are. So we need to have a notion of partition of space. So I have to go faster, right? Yeah, I'll be on time. So we have a partition. So we have a special construct for all points, which is the universal quantification, but instantiated by the finite set of the points. And what is a spread? A spread is something that contains 5 distinct lines. And these 5 lines, for some reason, I've missed something here. L5 missing some here. Okay, and all these spreads, they are computed externally. So I use an external tool to compute the spread and I return them in Coq. And then I have a statement which says that the spread I computed, which are stored in the list of list spread, it corresponds to all the existing spreads. So this proof is proceeded by induction on 5 variables, all these variables here, which are lines. So this means we have 52 million cases approximately. So it's a very difficult, it's a very long proof, and it takes about 1 hour or 1.5 hours to complete the proof. And when you launch QED, it takes another 1.5 hours, and in the end it fails with some weird exception. So we have one direction that's completely proven and validated by Coq, and the other direction is proved but not validated by Coq because the proof is too huge. And then we show that all these spreads are isomorphic. So being isomorphic means there is a collineation between, so 2 spreads are isomorphic if there is a collineation, which is a bisection which respects the incidence relation between them. So we prove that all these spreads are isomorphic, and we did that by going from the first spread to the second and the third one, and going back to the first one instead of having a general statement which takes 2 arbitrary spreads T1 and T2 and proves that they are isomorphic. In PG, concerning the packing, there are 240 packings in PG3.2. We managed to build them. We didn't show that there are no other packings, which is what is missing. And we managed to build the 2 classes of isomorphism, but we should still need to show that there are actually exactly 2 distinct classes, because we managed to make the collineation which allows the packing to be considered in the same class of isomorphism, but we didn't show that there are 2 and that there is not only 1. Okay, so the issues is to find an effective representation of both objects, both from a computational and formal reasoning point of view. So it put us in front of the limitation of Coq. So there are several solutions. One of them would be to enhance Coq abilities. So some bug reports allowed to enhance the Coq proof assistance, and the other way is to try and circumvent the limitation and do some clever stuff to make the proof simpler. So I will give some conclusions. So we managed to achieve some big proof about PG3.2, which meant pushing Coq to its limit. The next step, which are example of state-of-the-art result, will be to work on the packing of PG3.3, as did Beton in 2015, and some other works by made on PG3.4. And during this work, we also try and use some alternative prover. When we face the limitation of Coq, we consider maybe we can try with Lean or Z3. So with Lean, we got the same stack overflow or kind of similar errors when doing our proofs. And in Z3, we managed to have some SAT answer. Okay, thank you for your attention. And if you have any question, I would be more than happy to answer them. Thank you.
Thank you, Nicolas. Do we have questions? So please raise your hand if you have a question. Zoltan?
So thank you, Nicolas, for this great talk. I'm very impressed. Well, you mentioned that Coq is maybe not the best prover for this, and you want to try Lean or other systems. Maybe in the audience could answer this question: which prover should be the most fitting for this task? So I have the impression that this would be very nice to teach logic for students, maybe for prospective teachers. And I'm really impressed by this example. So I'm afraid that Coq is too complicated for students.
In this setting, we're using very simple data structure, but the amount of case to consider is huge enough, so it makes Coq fail. But when I tried alternative provers, I tried Lean and Z3. I don't know what's the way to pronounce it in English, because they are based on the same inductive definition principle. It's very easy. Like taking the code I wrote in Coq and putting it into Lean or into Z3, it's very easy. It's just minor cosmetic changes. Whereas if I try to use other automated prover, it's more difficult for me to understand how I deal with inductive types or how I simulate that I have inductive types which represent the lines and the points. So it was rather practical approach saying, okay, it doesn't work with Coq, something similar, does it work? And the answer is it doesn't work better with something like Lean. And my idea was to use formal proof in the way I find it convincing, meaning I want to make a proof which I can QED in the end, and I have the type checking which says, okay, it's correct. Whereas in Z3 or the other automated prover, I get something like SAT, which is a bit harder for me to get convinced it worked properly. But this is my
Thank you.
a bit of using Coq rather than other systems.
Thank you. Any other question? I do have one. So the proof are huge, but do you use without loss of generality or symmetries or tricks like that to try to reduce?
So I did use this kind of tricks in formally proving the axioms for projective space geometry, and I tried to use them in the proofs of spreads and packing as well, but it was more difficult because what is difficult is when you PG32 is the smallest projective plane, which means you can do something simpler. Otherwise, you will go in 2D instead of 3D. But and it's difficult to check because when you try something, it takes 1 hour to run. And so it's not very interactive to make experiments and things like that. But one idea is to go further in the symmetry and this kind of without loss of generality setting, which is what we do when we consider that the lines of the spreads are ordered in the system. To find the 56 spreads, we consider that they are ordered with lines, which force us to create an artificial order on lines, which is the one you expect, that L0 is smaller than L1. But for instance, this is not provided in Coq by default. If you do that in OCaml, the order of the constructor gives you the order relation. But in Coq, there is no order relation unless you define one explicitly. So that's what we did.
Okay, so thank you, Nicolas. Let's thank the speaker again. And maybe we can go for the last talk of today, which is by Nuno Beata and Pedro Quaresma about the Open Geometry Prover community project. So I think this talk is kind of related to Gilles' invited talk because it deals with how can we do prover sharing that works with several inner provers compatible with all what we have in our community, which is based on different geometry, different algorithm, and how can we share all this interesting stuff. So please, Nuno, you can maybe share your slide.
Okay.
It's okay. Okay.
Is everyone seeing the presentation?
Yes, it's okay. Thank you. We can hear you and we can see the slides.
Hello, everybody. I'll be presenting a project, the Open Geometry Prover Community Project, that Pedro Quaresma and I have been developing. As everyone who studies mathematics knows, proofs, more precisely mathematical proofs, are a cornerstone of mathematics. With the advent of computers and later on with the development of automated reasoning tools, specifically of automated geometry theorem provers, as these are the tools that matter to this project, these tools have enriched our experience with mathematics. But in order to avoid distinct efforts with the same goals, the development of these tools should be done in a coherent and well-organized community of researchers working in a collaborative way. Enters the Open Geometry Prover Community Project. It aspires to integrate the different efforts made by the community working in automatic deduction in geometry under a common umbrella. This effort intends to be a contribution to the goal of establishing a network of researchers working in the area of formal reasoning, knowledge-based intelligent software, and geometric knowledge management, and to explore efficient methodologies for the creation and reuse of electronic tools in geometry. To build such a framework, several tools must be implemented and protocols must be established. As of this presentation, Ogpcp has 5 goals. The first goal is to provide a common open access repository for the development of GATPs. This is an obvious goal, as every prover should ideally be available to researchers. The second goal, to provide an API that every GATP should ideally adhere. The reason being that this way provers will be easier to be used, either as standalone tools or integrated in other tools. Third goal, the development of portfolio strategies to allow choosing the best GATP for any given conjecture. The fourth goal, to interface with the repositories of geometric knowledge. More precisely, we're thinking about TGTP, the 1,000 of geometric problems for geometric theorem provers repository, and TPTP, the thousands of problems for theorem provers repository. Finally, the fourth goal is to develop a competition between GATPs to be able to rate them. In its current implementation, Ogpcp works as follows. It is composed of four different modules. We have the filters that are used to convert between conjecture formats. For example, if I want to convert a GCL conjecture to the format, a filter must exist. We then have the post-processor module. The reason being that provers that do not follow rules, Ogpcp rules, in particular, their output doesn't need to follow these rules. So these post-processors are used to extract information from the prover's output so that it can be used by OGP. Then there's the provers module. Obviously, that's where all the provers that are part of Ogpcp, the native provers, are located. Finally, there's the OGP module, which is basically one program that handles all the details between all these modules, filters, post-processors, and provers, as well as external provers like GCL, Vampire, and external repositories. Everything done in a consistent way. The first goal about the source code, Ogpcp code is available at GitHub, and it's licensed under GNU GPL 3 or later. We supply just source code. Its installation is a simple process as long as tools like Ant, Make, OpenJDK, C compilers, C++, Flex, and Bison are available. The installation process hasn't been automated yet, but we intend to do it very, very soon. Regarding the API, the second goal, the Ogpcp API is a set of command line tools prepared to work together. They comprise the provers, the filters, and the post-processors. Ogpcp provers, native provers, must follow some rules. Namely, they have to use TPCP's first order format for their conjectures. This is the FOF that I mentioned earlier. Accept the same command line arguments and provide the same output. All these details will be explained in Ogpcp documentation. As for external provers developed by other teams, they don't have to follow any of the Ogpcp rules, but they should provide filters to convert between FOF and the prover's format, and the post-processor to interpret the prover's output. Filters and post-processors exist. Namely, there are filters to convert from GCL to FOF, GeoGebra to FOF, and JGEX to FOF. Now, a conjecture can be described by a FOF formula, but if we want to use a generic theorem prover such as Vampire, which uses FOF, we must supply a set of axioms. Currently, we are using the axioms of the deductive database full angle method described in an article by Shu, simply because they've already been converted to the FOF format. As for post-processors, they exist, and right now they just try to find if the proof was successful or not. The third goal, the GATPs, several external GATPs can be used by Ogpcp simply because filters and post-processors have been written. Among them, we have the GeoGebra automated reasoning tools, GCLC automated reasoning tools, and JGEX. Others, such as the Cox implementation of the area method, will soon have filters and post-processors. Generic theorem provers can also be used, but of course, filters and post-processors must be written to be able to use them. Internal provers. Regarding internal provers, Ogpcp has the provers from the OpenGeo Prover project. It's not the OpenGeometry Prover, it's another project, OpenGeo Prover project, which implements the VUS method and the area method. But both these methods have some problems. A new prover using deductive database method is in an implementation stage, and we are researching on another new prover using deductive graphs method. Regarding portfolio problem solving technique, where to solve an individual instance of a problem, the most adequate solving technique is hopefully chosen and applied. For the area of GATPs, work has already been done by Kovacs and Mladen Nikolic. And they have been implemented in the GeoGebra prover mechanism. We also hope to incorporate this research in Ogpcp. As for external repositories, a client-server architecture. As for repositories, a client-server architecture to connect to TGTP, just to GTP, exists. In fact, right now, the TGTP repository is listening to client requests. The code is also available as part of the Ogpcp and is at GitHub. Finally, the last goal of OGP, the GASC, the Geometry Automated Theorem Provers System Competition. Its objective is not only to compare proving methods and its implementations, allowing the exchange of ideas and algorithms, but also to push towards the standardization of conjecture formats and the creation of sets of tests. The competition will also allow people to choose a GATP best suited for their goals. For example, the fastest prover, or the prover with the best visual proof. Later on, tomorrow, the last event of the morning, GASC 0.9 will take place. Now, considering that the integration of different GATPs is not an easy task, different algorithms and provers do not assume the same mathematical setting. Indeed, we can have different geometries, different axiomatics, and different approaches. It is probably unrealistic to aim at a full integration. So, Ogpcp aims to provide a simple, open source, and well-documented API, and constitute itself as a forum about automatic deduction in geometry. Thank you for listening. I'm now available to answer any questions you may have.
Thank you, Nuno, for this interesting talk. So do we have questions?
Okay.
Zoltan.
Thank you for this nice talk, Nuno. I learned that you worked a lot during the last 2 months on this project. Can you quickly summarize what kind of updates you did during the last weeks?
During the last weeks, not much.
Okay.
Before holiday, I did. Yes, I did work. Basically, the problem with this project, there are lots of tools and small tools. Nothing very, apart from the provers, nothing is really complicated. But there are lots of small tools to write and test. And that's what has been taking me a lot of time, because I want to, sooner rather than later, have Ogpcp to be able to be installed in a Unix system in a easy way, using known GATPs like GCLC, GeoGebra, and the Coq area method. So I'm pushing towards that, and at the same time working on the prover using the detective database method and the graphs database method.
Okay, thank you. And you will do the competition tomorrow?
Yes.
Really? So we can be prepared for some real contest?
Yeah, well, it's not GASC 1.0. We wish that, but it's not still there. So there are lots of problems to be solved. and I will try to explain them some of the problems that we have. Some we have solutions or partial solutions, not the best solutions. So, well, whether one can consider that.
Okay, I'm looking forward to hearing the results. Thank you.
Any other question? I do have one. I think you were planning to talk about it, but it was almost your last slide. I think one of the big problem of either the competition or the community project is that we have tools working in different theoretical settings and trying to have different goals. So we have algebraic provers,
yes.
We have provers in synthetic geometry, we have the RR method which assume geometric construction and with some specific construction tools and so on. So what is your plan to merge all this? Do you have an idea, or you can compare such different things?
I didn't understand. What's my plan to
translate, I think, a statement from one theory to the other, or to check if it's if the prover is compatible with the statement you want to try, and so on. Because it's difficult to have a general input for such different systems.
Yes, and I must say that I haven't think about that. We are in a previous phase. We haven't yet think about that.
Okay, thank you. Any other question? So maybe I give back the Zoltan. You can say, when do we start? We start at 2 p.m. this afternoon.
Yes, exactly. Thank you for this nice morning session. Thank you for your efforts in the chairing, Julian. So I enjoyed this morning time. And yes, exactly, we will continue at 2 o'clock. So you can have a longer lunchtime. Thank you for attending ADG, and see you hopefully soon in 2 hours.
Thank you. Thank you for the speakers. See you later.
Okay. Bye.
Bye.
Bye.